In this video, we discuss transformer overexcitation and introducing Beckwith M3311 transformer protection relay. When an external magnetizing field H is applied to the material, it penetrates the material and aligns the domains, causing their tiny magnetic fields to turn and align parallel to the external field, adding together to create a large magnetic field B which extends out from the material. This is called magnetization. The stronger the external magnetic field H, the more the domains align, yielding a higher magnetic flux density B. Eventually, at a certain external magnetic field, the domain walls have moved as far as they can, and the domains are as aligned as the crystal structure allows them to be, so there is negligible change in the domain structure on increasing the external magnetic field above this. The magnetization remains nearly constant and is said to have saturated. Different material has a different saturation point. Transformer cores usually made from silicon alloy. Generally the transformer knee point is about 1.1 to 1.2 Tesla. In normal operation, the generated flux remains in linear part of transformer magnetization curve. The waveform distortion is minimum in the circumstances. Increasing voltage at transformer terminals pushes the transformer in nonlinear part. In nonlinear part, transformer distorts the waveform. Because the saturation curve is symmetrical, it generates the symmetrical distortion. Fourier transform of symmetrical waveform contains odd harmonics. Third harmonic will be illuminated in delta windings. The next odd harmonic is the fifth harmonic. Increasing in fifth harmonic is a good sign of the transformer overexcitation. Overexcitation can be a transient phenomenon. Transformers close to generators are in danger of overexcitation mostly due to AVR overshoot or faulty AVR. However, if transformer overexcitation is not temporary, transformer overexcitation protection should trip the transformer. Transformer positive sequence impedance can be modeled as this picture. All impedance are transferred to primary for easy calculation. In this model, the primary current is a summation of magnetization current and secondary current. The magnetizing branch contains a nonlinear impedance to model the transformer core saturation. When the voltage across the magnetizing branch is higher than knee point, its impedance drop to very low value and it will increase the magnetizing current. Transformer differential relay will neglect magnetizing current as it is very small value in normal operation. But during overexcitation, this value is not negligible and can push the relay to trip during a transient overexcitation. In normal operation, the differential current is very low, and differential relay is stable. To simulate overexcitation, an event of transient overvoltage has been generated. As we were expecting, the differential current has increased dramatically. The ratio of the fifth harmonic differential current to fundamental differential current is about 22% in this example. The high differential current can push the relay to trip. By setting the fifth harmonic blocking value lower than 22%, we can avoid such nuisance trip. 22% is the upper limit for this example. There is the lower limit for setting fifth harmonic blocking element. During a heavy fault, current transformers get saturated. As we see, the saturated transformer is generating the fifth harmonic. The lower limit for the fifth harmonic blocking is to avoid relay blocking during the fault. During the heaviest fault, the fifth harmonic content of differential current is about 13%. So the setting has to be somewhere between 13% to 22%. 15% is the advised setting for this system. Beckwith M3311A is the Advanced Transformer Protection Relay. It can protect transformers with 2, 3, or 4 windings. Beckwith M3311A provides dual slope restrained differential, high set unrestrained differential and restricted earth fault differential elements provide excellent unit protection. Unique second and fourth harmonic restraint for enhanced security on transformer energizing. Fifth harmonic restraint for security during overexcitation events. Overexcitation volts per hertz element for extended asset protection. Undervoltage and underfrequency elements for load shedding applications. Phase and ground overcurrent elements for backup protection. Breaker failure protection and breaker monitoring for each winding input. This is how to set the fifth harmonic blocking on Beckwith M3311A.